So far in life, you've learned how to integrate over intervals, regions in the plane, three-dimensional regions, and curves. The last kind of integral we're going to learn about is a surface integral. Unsurprisingly, this is when the object that we're integrating over is a surface. Just like with line integrals, in some sense there are two different kinds. There's a scalar surface integral where the function you're integrating is scalar valued. And then there's a vector surface integral where the function you're integrating is a vector field. In this video, I'm just going to talk about scalar surface integrals. But in general, there's a lot of parallels between scalar and vector line integrals. As usual, before we do some examples, I want to go over the main steps for evaluating one of these scalar surface integrals. We'll be given an expression like this, where we'll see a double integral sign, a scalar valued function, and then typically something that looks like d capital S. That d capital S is one indication that we're doing a surface integral, but also usually the context of the problem will tell you that S, the thing under the integral signs, is a surface. The game plan here is the same as with line integrals in the sense that we have a curvy object that we're trying to do calculus on, and that's hard. We don't know how to do that. But we do know how to do calculus on flat things. So what we want to do is we want to find a function from the flat world, which usually we'll use u and v to denote the flat two-dimensional world. And I want this function to eat some two-dimensional region in the uv world and spit out my surface. And we'll use this function to translate the calculus problem on the surface to a calculus problem on a flat thing, where things are easier. Now, this process that I just described is exactly parameterizing the surface. This time around, parameterizing looks a little different than in the one-dimensional case because with a curve, you only need one parameter to describe a one-dimensional thing. But with a two-dimensional object like a surface, you need two parameters. But nevertheless, this is still a parameterization of the surface. So this is your first step. Write down a function g of two variables, which gives you the surface. And also like before, when you write down a parameterization, you need to specify the parameter domain. This time, instead of being an interval, it's going to be some region in the two-dimensional world. Your second step is to compute the normal vector at every point on the surface. In particular, you want the normal vector given by the cross product of the partial derivatives of g. I'm not going to talk about this too much in this video, but the partial of g with respect to u and with respect to v, these are tangent vectors to the surface. And they measure how much the surface is being stretched and contracted by this map G. So this normal vector that we're computing encapsulates all of this information about stretching and contracting. You can think of it as being like a Jacobian type thing. Anyway, it's just something to compute. And once you have that, you can take the surface integral and turn it into a normal double integral. How do you do that? The region for your double integral is going to be the parameter domain. So whatever the region E was in the UV world, that's what we're integrating over. Then you transform F by just plugging in your expressions for X, Y, and Z. and then you multiply by the magnitude of the normal vector. Again, the analog here in the line integral case is multiplying by the norm of r prime. Here we use this normal vector instead. And there you go. Abstractly, this expression that I just wrote down looks a little complicated, but in reality, it's just going to be a two-variable integral, a regular old double integral, and at this point in your calculus career, that won't stand a chance against you. I have a couple examples lined up to give us some practice with parameterizing surfaces. Like with the line integral case, typically the most difficult part about these problems is going to be parameterizing correctly. Once you do that, it's just a matter of computing the things you need and setting up an integral. And given a surface, there are many different techniques and tools that you can use to parameterize it. So I want to describe a handful of them in this video. With this first example, I'm actually going to give you two different solutions. At some level, they're the same, but technically they use different parameterizations. But anyway, I'll talk about that once we get to the second solution. So here's the example. We have a surface which is defined by some equation, y equals x squared plus z squared. And we're given this condition that y has to be less than or equal to 4. The surface integral we want to evaluate is the surface integral of the function 1 over this surface. The first observation I want to make is one that will come up a lot, and it's the following. I notice that y is a function of x and z. This means that I can just use x and z as my parameters. And once I do that, y is determined for me. I don't have a choice. This kind of thing should sound familiar at this point. And in general, whenever you have one variable as a function of multiple variables, in terms of parameterizing or whatever, you can just use the independent variables as your parameters, and then the new variable is determined for you. Anyway, so one thing we could do is we could call x u and z v. And then, like I mentioned, at this point we don't have a choice. Y has to be u squared plus v squared. This is going to give us a formula for the parameterization, but we need a domain for our parameters, and this is going to come from the condition that y has to be less than or equal to 4. This forces u squared plus v squared to be less than or equal to 4. And that expression right there is the parameter domain. That's a disk of radius 2 in the UV world. That's the region E that I was describing earlier. And there we go. So let me write this down as a g function. A parameterization of the surface is going to be g of uv is x is u, y is u squared plus v squared, and z is v. And then, like I mentioned, the domain is u squared plus v squared is no bigger than 4. That was step 1. Step 2 is to compute the normal vector. This is going to be the cross product of the partial of g with respect to u and the partial of g with respect to v. So the partial of g with respect to u is a vector. The first component is the derivative of u, which is going to be 1. And then the derivative of u squared plus v squared is 2u, and the derivative of v is 0. Cross, and then likewise for the v derivative, I'll get 0, 2v, and 1. And then also, as usual, compute the cross product however you want. You should get 2u, negative 1, and 2v. And now we're ready to transform the integral. The original integral is the surface integral of 1. When we convert this into a double integral, our new region of integration is this u squared plus v squared is less than 4. 1 stays 1, nothing changes there. And then I multiply by the magnitude of this normal vector that we computed. So computing this magnitude is going to be the square root of 4u squared plus 1 plus 4v squared. And before we move on, I just want to reiterate, because this is an important conceptual and organizational thing to keep in mind. At this point, this is just a double integral. From here on out, this is something you could have done a month ago. Doesn't matter that we started with a surface integral or anything like that. This is just a double integral, and we can use any double integral techniques we want to evaluate it. In particular, it seems like polar coordinates might be a good idea here. We're integrating over a disk, and I also see a u squared plus v squared type expression in my integrand. So that's what I'll do. I'll change to polar coordinates. I'll call u r cosine theta and v r sine theta. And then there's no surprises here. This is a disk, so the bounds are going to be from 0 to 2 pi for theta, and then 0 to 2 for r. The integrand, if I collect these u squared plus v squared terms, I would get a 4r squared and then this plus 1. And then we've changed variables, so I have to multiply by the Jacobian, which is r. So I get r dr d theta. And now we can finish it off. I'd probably do another variable substitution in the single variable sense, where I call this stuff under the square root a new name. We're running out of letters to use, so I guess I'll call this s. Then ds would be 8r dr. So r dr is 1/8 ds, so I pick up a factor of 1/8 out front. Theta is still going from 0 to 2 pi, and then s, my new bounds, when r is 0, s is 1. When r is 2, s is 16 plus 1, which is 17. The integrand simplifies to s to the 1/2, and then this is a very straightforward integral to do. Like I mentioned, I want to give you another solution to this problem. I want to do this just to give you a couple different perspectives on the same process and how they fit together. So to do that, let me recap the solution we just did with a picture. In my head, the way I'm thinking about what we just did is we have this surface that we started with, y equals x squared plus z squared. And in the first step, we found a map G from a disk in the UV world, which spat out this surface. That was our parameterization. Then we did our thing and we set up a double integral, but then we had to change variables again. In order to evaluate it, we had to make a polar coordinate change. So there's kind of another step here from the r theta world via a polar coordinate change map to the disk. Then from the disk to the surface via G. And that's great, there's no problem with what I did, but if you think about it this way, you could wonder, what if we did this in one step? What if instead of parameterizing with u and v over this disk, what if I composed both of these steps and came up with a new parameterization from the rectangle in the r theta world? Where now I would be thinking about my parameters as r and theta. Then maybe we could do everything above in one go. And wow, Joe, you're right, we can do that. This is what my second solution is going to be. I'm going to write down a completely different parameterization, which is in some sense the composition of the two steps from above. This should seem like a good idea anyway, just because when you look at the equation, y equals x squared plus z squared, that x squared plus z squared feels like a polar coordinate type expression. So my new parameterization, I'll call G2. The parameters will be r and theta. X, I'll call r cosine theta as usual. But then I'll call z r sine theta because in this expression, x squared plus z squared, z is kind of acting like y normally does. And then again, like before, now that we've determined what x and y have to be, we don't have a choice. If y is x squared plus z squared, y has to be r squared. And again, we get a parameter domain defined by r squared is less than or equal to 4. This places no restriction on theta, so theta will go from 0 to 2 pi, and then r would range from 0 to 2. That will be our parameter domain. And then we can proceed as before. We have a parameterization, so the next step would be to compute the normal vector. This time we'll take the partial derivatives of g2 with respect to r and theta, and then we'll take their cross product. The derivative with respect to r is going to be cosine theta, 2r, and then sine theta. And then we take the derivative with respect to theta, and so we get negative r sine theta, 0, and then r sine theta. We can take their cross product. Again, do that however you want. You should get 2r squared cosine theta, then negative r sine squared theta minus r cosine squared theta, and then 2r squared sine theta. Then, like before, we're ready to convert the integral into a double integral. The parameter domain was theta goes from 0 to 2 pi and r goes from 0 to 2. 1 is 1. And then we have the norm of this new normal vector. So I'll multiply this expression out and we'll get 4r squared cosine squared plus r squared plus 4r squared sine squared. We can do some simplification. One thing I'll do is I'll factor out an r squared through the square root. That would give me an r out front. Then I'll have the square root of whatever's left. Well, underneath the square root, I would get a 4r squared times cosine squared plus sine squared, which is 1, so that'll leave me with 4r squared, and then a plus 1 from that other term that I pulled an r squared out of. And look what we got. We got the exact same integral that we got above after making the polar coordinate transformation. There should be no surprises there because this parameterization that we wrote down really was the composition of both of our steps above. So it really is the same, it's just a different way to think about it. But the other reason why I wanted to show you this solution is because if you do something like this, sometimes it can be a little tempting to think, oh, should I add an extra r dr d theta? It's kind of a gut reaction because you're so used to doing that after changing coordinates to polar coordinates. But the answer is no, you do not need to do that here because we did not ever do a change of variables. We accounted for everything with this parameterization. So if you do something like this, there's no need to add in the Jacobian just because you're working with variables that remind you of polar coordinates. Anyway, another perspective on the same solution. Okay, I've got one more example. Hopefully we can get through it without me falling asleep because it's way past my bedtime right now. So in this example, S is the portion of the cone z equals square root of x squared plus y squared in the first octant contained in the ball x squared plus y squared plus z squared is less than or equal to 1. So we'll figure out what's going on there in a second, but it's some surface. And what we're supposed to do is evaluate the surface integral of z squared. Now, as a remark, you could do either of the two things that we did in the previous solution. You could parameterize this by just calling x and y u and v, like in the first solution. Or you could look at the x squared plus y squared term and think, oh, maybe I'll do polar coordinates and mimic what we did in the second solution. And I think both of those should work out pretty fine. It's a good excuse to get some more practice, and you should get the same answer that I do at the end. But just for the sake of variety, to show you a couple different ways to think about how to parameterize surfaces, I'm going to do something slightly different. It's not drastically different, but it's a good kind of technique to keep in mind. So here's my new thought process. The fact that this surface is partially cut out by a ball makes me feel like spherical coordinates. So maybe I can parameterize this using a spherical point of view. Now that's vague, I'll explain exactly what I mean by that. But the first thing is to note that the equation of the cone, z equals x squared plus y squared under a square root, what do we get when we turn this into spherical coordinates? Well, we get rho cosine phi, and then the square root of a bunch of stuff that I'm too tired to read out loud right now. But we've done these kind of computations before. Simplify some of the trig functions and you'll get rho squared sine squared phi under the square root, which then gives you the equation rho cosine phi equals rho sine phi. Divide through by rho, you get cosine phi equals sine phi, and this happens when phi equals pi over 4. So we've seen this before, and it should also make sense geometrically. The equation of a cone like this is the constant angle phi equals pi over 4. So here's the point. Spherical coordinates give us a way to describe any point ever in space. So all points in the world can be written in the form rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. But we're not trying to describe every point ever in the world. We're only trying to describe the points that satisfy phi equals pi over 4. So what if we just take the expression for spherical coordinates that describe all points, and I impose the restriction phi equals pi over 4? In other words, I'm just going to plug in pi over 4 for phi in these spherical coordinate expressions. That's going to give us a parameterization. Here, the parameters are going to be rho and theta because phi is fixed, phi is constant, it's pi over 4. Sine of pi over 4 is root 2 over 2, so x is going to be root 2 over 2 rho cosine theta. Likewise, y is going to be root 2 over 2 rho sine theta. And then cosine of pi over 4 is also root 2 over 2, so z is going to be root 2 over 2 rho. Also, as usual, I need to specify a parameter domain. Well, rho is going to go from 0 to 1, and theta will go from 0 to pi over 2. The 0 to 1 bound for rho is coming from the ball thing. This says exactly that rho has to be less than or equal to 1. And then the theta bounds were coming from the fact that we're told that we're in the first octant. So that's defined by theta going from 0 to pi over 2. And there we go, we've got a parameterization, we've got a parameter domain. So now we just stumble through the computations as usual and we'll be done. We need a normal vector. We'll take our parameterization, compute the partial derivatives with respect to rho and theta. Now, in this vector, the components have a common factor of root 2 over 2, so for each of these derivative vectors, I can just pull that factor out. That will save me about 7 seconds of my life. And then once we do that, the rho derivative is going to be cosine theta, sine theta, 1. And then the theta derivative, if you haven't fallen asleep yet, you'll notice that I'm about to forget to write the rhos. And I'll catch it in a second. And instead of editing out that mistake along with the other 15 minutes of mistakes that I make, I'll leave this one in just so that you know that I am not, in fact, an invincible mathematical deity. I do every once in a while make a mistake. Then we take a cross product. These factors of root 2 over 2 you can pop together to get a 1/2. And then the cross product should be negative rho cosine theta, negative rho sine theta, and rho. And then from here there's nothing fancy. Set up the integral. Bounds go from 0 to pi over 2 for theta and 0 to 1 for rho. That came from the parameterization. Now, z squared, the function z squared, we have to change with our new parameterization. The z component of the parameterization is root 2 over 2 rho. So we get that expression squared. Then I multiply by the norm of the normal vector.